Who in here has heard of RAG? By a show of hands, awesome. And then who has implemented their own RAG system or used a RAG system? Okay, fair few hands. So we're going to be talking about RAG. To the best of my knowledge, this is the first public publication related to SAR and RAG combined, which is pretty cool, or at least SAR for ATR. And so we're going to be talking about how to set up such a system and some of our benchmarks compared to some of our other implementations. So the problem statement here, it's a pretty general ATR framework. We're going to take SAR chips. We're going to try to classify them. Perhaps we're going to do other more advanced techniques such as visual question answering. Maybe we want to ask questions like, what kind of military vehicle is this? And allow a multimodal large language model to generate a longer caption with information, or perhaps relevant information that's observed in the larger scene. And so that's some of the capabilities that we're exploring right now. And some of the shortcomings right now are when you train a multimodal large language model, it's pretty static. A few years ago, if you used ChatGPT, they had this cutoff date where it was only trained with a certain amount of data, and that data might have been a year or more stale. And so we would like to have new information, the best, most relevant, and up-to-date information available for the model to use. And RAG really enables such a system. And additionally, you get the benefits of a grounded system, something that you can compare to other known true values, and a data-efficient solution. And we'll be talking about that a little bit more. So at a high level, this is some of the architecture that we're going to be discussing. As I mentioned, RAG, Retrieval-Augmented Generation. So we're going to retrieve context. We're going to augment our input to the multimodal large language model. And then we're going to allow it to generate an improved response with that additional context. So there's a retrieval module. We're going to be talking about that a little bit. We evaluate the system in similar ways to the standard model, accuracy and other sort of comparison methods. But also there's other more advanced retrieval metrics that we're going to be talking about a little bit. And so there's some specifics here related to retrieval-augmented generation. So that's mostly the focus of this talk. I gave a talk earlier today that talked a little bit more about the multimodal large language model that we're using in our different systems. And then our paper from last year detailed some of the implementation of the model itself. So there's lots of benefits from the SAR-RAG. And but why would you want to do that? We talked about that a little bit already. There's a static model. We want to create something that's dynamic. We're going to give it grounding. It's going to be a little bit more robust to noise. If we've got things that are unusual, outliers, perhaps it's similar enough to things that it's seen in the past that we can ground it to something that's true and accurate. So we're anchoring those predictions to real observations that we've labeled in the past, which enables interpretability. And this can be used not only with just imagery, but perhaps also with imagery plus question of interest. So what are the characteristics of this vehicle versus what type of vehicle is this? If you provide both the question and the relevant image, you can tailor both of those to generate a very particular embedding, and that embedding can be then compared to other things in context. And that's another interesting point that I'll make later. So here's a little bit more detailed systems architecture. We're going to provide a user query. You could provide a lot of different questions asking it to the sort of chatbot interface, or you could provide a standardized sort of questions. These are my 20 top questions that I care about. These are the most interesting things for ATR contexts. I want to know the size of the vehicle, the weight of the vehicle, the shape of the vehicle, the length of the vehicle, the height of the vehicle, the length of the weapon system on top of the military target. All of these things are things we've trained into our model. And so that question, along with the unknown image that's coming in, both of those are going to be embedded at this step 2 multimodal embedding. That's going to create this vector that's going to point you towards other relevant examples that we've seen in the past. So that queues up the retrieval module on step 3. To implement that retrieval module, we have a vector database. A pretty standard quadrant database is the publisher, or excuse me, the company that produces the technology. And so that very quickly we can gather the most related vectors, and we don't have to compare against all of the vectors in this potentially very large set of previous examples that we might have observed. So we're going to retrieve context, perhaps the most relevant, closest matching vectors. We're going to provide that to the multimodal large language model, and we're going to get an improved output through that process. And so that we can see improvements in accuracy and in some of the other metrics that we measure. Then perhaps you have an analyst review the outcomes, see if it's true, and provide a feedback loop where you could train your machine learning mechanism, right? You could train your large language model or your image embedding, but perhaps you just want to re-rank your vector database, and that's a different technique. And so you can do that on the fly. You don't have to do a large training regime to re-rank your vector database. Okay, so here are just some image embeddings, some of the standard MSTAR targets of interest. We've got different Soviet-era military vehicles, and you can see they're sitting all on top of each other in this large cloud of embeddings. And so it's not like we have great separation here. The image embedder here is not trained particularly well for these targets of interest, but we allow the language model to interpret these in different ways. So what we do find is we can still point our vectors through our embedding mechanism, and it will point towards similar examples at a certain degree of accuracy. And that improves our accuracy overall. So even though we have targets that look very similar in this context, we're still able to at least cluster on the majority to things that are relevant and related to our target of interest. So just taking a step back really quickly, I want to introduce some of the technologies here related to large language models and the image embedding mechanism. So people have heard of transformers, a type of neural network for language relationship modeling. You could train something like this through a generative pre-training process. This is a mechanism where you just allow the language to learn on internet data and just generate text sequences. And this produces a language encoder and a language decoder as sort of an autoencoder mechanism. Then we take these mechanisms, we take this language encoder, we then align this to our vision encoder. And the vision encoder could be anything. We're using a vision transformer, but it could just as easily be a ResNet or a mobile net or a YOLO or whatever you want to use as your vision encoder. There's things that are better than others, but we align the language and the vision so that they're speaking the same language in a sense. Our vision encoder now produces tokens, it produces vectors that are in the same style, in the same semantic understanding of language. And so then we can take this language encoder and this vision encoder as well as the generatively pre-trained generator. We take all of these elements, we combine them into a unified architecture, and now we can leverage the capability of all of those systems combined. And so we can pass in language, we can pass in imagery, they're embedded into a similar context, then we provide that to a generator, and we can produce answers trained by our data set of interest. And so that data is the MSTAR mixed target data set. It's a little bit dated at this point, but it's still an interesting benchmark for us to use for SAR. There's not a ton of image examples here, but we can still do some interesting tricks to generate more labels than we might otherwise had if we were just doing classification. We take metadata of interest for all of these targets. As I mentioned, the size dimensions of the vehicles themselves, how big is this vehicle, how long, how tall, how wide, what type of weapon system is on the top, what are other metadata characteristics. We teach all of this language with the blind image chip, and it starts to learn these patterns with the images in context. And so all of that learning happens in the multimodal large language model, but our RAG implementation here, as I mentioned, we're going to take that vector database, we're going to encode down into the latent space, we're going to store all of those vectors in this quadrant vector database. Using cosine similarity, we're going to look up other things that we've seen in the past. That would essentially be your training data. And in that way, we're getting two uses out of our training data. On the one hand, we can train it into our machine learning system. We can train it into our multimodal large language model. On the other hand, we can also reuse it as ground truth within our vector database. And so that becomes a second use of the training data within this RAG system. And so that allows us to recall something from the past that we've seen, and our evaluation data, our test data that's held in the blind, then would relate to some of those image chips that we have seen in the past. And we see that it's able to recall prior examples. And so I detail some parameter efficient fine-tuning techniques in some of our previous work, but that's necessary here if we want to train on like a single GPU setup. But we can still train a pretty powerful large language model. So here are some of our evaluation metrics and results. In the small print here on the side is our table that we're going to release in our paper. In the top, we've got evaluation metrics which relate to classification. We've got accuracy, at the top, we've got evaluations that relate to retrieval. And so our RAG system needs to find other relevant examples. So if we provide a blind image of a T72, we want it to get similar examples of T72s. Perhaps we're filtering some of our previous observations by the observation angle, perhaps any other metadata that we can put the SAR chip in context. But then we recall from our vector database to this retrieval, and our accuracy at one shot, about 77%. So that we have some degree of inaccuracies where we have a chance to pull something that's not our target of interest, and that would lead us astray. But if we take several examples, perhaps 5 examples, more often than not, we get a majority consensus amongst our retrieved information, and that allows us to make improved decisions about what we think we might be viewing, and we can generate improved results based on that. So after these retrieval metrics at the top, then we go into some of our more interesting metrics related to vehicle classification. We can generate a qualitative set about the vehicles. Is it an amphibious vehicle? Is it an artillery system? Is it a main battle tank? Is it a tracked vehicle, a wheeled vehicle? Is it a transport truck? All of these other qualitative descriptor words, we've taught that into the model, and it can associate those with chips, independent of a classification. So you don't even need to tell it what classification it is. It will estimate what are the characteristics independent of the class. And so besides those classification, I call them classification, but it's sort of every one of these different characteristics, we might say, is a independent classification binary. We also want to estimate the dimensions of the vehicle, as I said. And so we estimate the vehicle's weight here, and then all the other vehicle dimensions are in the metrics that we're using here: mean absolute error, root mean squared error, And then one that I find to be most interesting is the mean absolute percent error, or mean average percent error. Whether we're measuring in tons, that's a 40-ton tank, or that's a 60-ton tank, or that's a 5-ton truck, the percent error allows us to relate it to tonnage. And we can take that metric and relate it also to measurements such as the length of the weapon system in meters, or perhaps those are the two metrics that we use most often, is tonnage and distances. Okay, so those are meters and tons, and so we compare all of those error metrics between what if you just guessed randomly amongst potential targets, right? There's a lot of tanks in here. You could just say it's a heavy tank. And so what would you get if you guessed randomly, or you used some sort of average value? And so the column on the right is random guesses weighted by the probability of that class relative to the whole. And so even if you had an oversampled class, an unbalanced data set, that weighting of the random variable there on the right is still accounted for. And so in the middle is our baseline. It's the prior work that we presented last year. It's the journal paper that we're hoping to release soon, and some of the other work that we've done on the side. And then the new system, this SAR-RAG system, shows minor improvements above the baseline. It's getting close to 100%, so it's hard to really measure it precisely. But we're gonna try to evaluate this system against a harder data set here pretty soon. And so this was more of a proof of concept than a really robust evaluation against a lot of other comparisons. And so yeah, we're getting close to the end here. I talked a little bit about the evaluation metrics, and we compared against our previous baselines. In addition, I broke it. Here are those papers that I mentioned. At the top is a paper that we presented last year. The VQ ATR is a journal paper that we're working on right now that starts to talk about this quantitative estimation of vehicle ATR characteristics, and then the SAR-RAG system that we just talked about. So they all use the same method, the same multimodal large language model. So we've tried to keep that consistent so we can do an apples to apples comparison here on the right. And so in the top is our initial work that we presented last year. This VQ ATR is the journal paper, and at the bottom, the SAR-RAG system, which shows minor improvements over the baseline. So in conclusion, there's a lot of interesting things you can do with this RAG system. You can get that context to maybe you can find a majority of similar images, and that can help inform your large language model to make better predictions. It's more data efficient, as I mentioned. You're reusing the data not only for training, but also within your database. And so you will never forget those examples again. You will never accidentally unlearn those as you learn new examples. They will always be persistent within your database, so long as you keep them there. You might choose to purge examples out of your database as you get more examples. But these vector databases are pretty robust, and they scale well with the quantity of data. That reduces your retraining cost. You don't need to retrain your machine learning system quite as often. And so you can get away with just updating your database, which is cheap. The sensor, in particular, can now become a little bit more context aware. And so when we retrieve information from our database to find previous examples, we can say, I want to only look at graze angles of a certain filtering mechanism. So I can find vehicles as they would appear in distorted SAR imagery from a particular graze angle. And so there's different things that we can do or explore there. So lots of cool things. I hope to apply this to some new data here after this proof of concept. So thank you very much, and open for questions.